Bienvenido a un nuevo evento de Cátedra Europa.
Good morning and good afternoon to those joining us from the UK. On behalf of the 24th edition of Cátedra Europa, we welcome you to the session Biomass Valorization and Bioenergy Impact, for which we have the special participation of Drs. Andrew Welfel, Angela Miñas, Antonio Bula, and Samira Garcia. We will now leave you with Dr. Bula. He is the chair of the Mechanical Engineering Department at Universidad del Norte. He's a senior researcher from the Science, Technology, and Innovation Ministry in Colombia. He's also a member of the American Society of Mechanical Engineering since 1997 in the Advanced Energy Systems Division, where he served as division chair from 2015 to 2016. He's the author of 6 books and more than 100 papers and proceedings. Dr. Bula will be presenting our guest and moderating the session today. We welcome you all. Professor Bula, the floor is yours.
Thank you, Gary. Let me first say thanks to all of you for coming to our conference on biomass valorization and bioenergy impact. We will have the opportunity to hear and interact with 3 researchers from the United Kingdom and Colombia. I want to thank especially to our guests, Angela Miñas and Andrew Welfel from the University of Manchester, and Samira Garcia from Promigas in Colombia. They will give us a conference considering different aspects associated to biomass and bioenergy from the United Kingdom perspective, technical view, and social impact. Now, let me just give a brief introduction about our speakers. Dr. Andrew Welfel from the University of Manchester. He's a research fellow at the Tyndall Center for Climate Change Research at the University of Manchester. He has a background and interest in environmental, energy and engineering, and a strong track record undertaking sustainability, climate change, and bioenergy research through developing modeling toolkits and analysis methodologies. Furthermore, he is a topic representative within the current United Kingdom SuperGen Bioenergy Hub research program, where he works with academics, non-governmental organizations, industry, and government to promote the growth and sustainable UK bioenergy sector. Andrew is also the author of the University of Manchester's Bioenergy Impact Case that demonstrates how Manchester's bioenergy research has provided the science on which UK policies have been developed to support the deployment of United Kingdom low-carbon heat bioenergy technologies. We also have Dr. Samira Garcia from Promigas here in Colombia. She has conducted interdisciplinary research on the technical, environmental, and economic feasibility of deploying bioenergy technologies using agricultural residues to provide low-carbon energy. After finishing her PhD, she worked as a research associate and consultant in the Tyndall Center for Climate Change and Research, where she was involved in evaluating the feasibility of bioenergy with carbon capture and storage technologies for greenhouse gas removal in the UK. Currently, she is a professional in research and innovation in Promigas at the Center for Research and Innovation in Energy and Gas. She handles different projects aimed to innovation and technology development within the company in topics related to energy and natural gas. Her research interests are on development of sustainable bioenergy, integration, using residues and waste, mainly in the global south. She's also researching in how to overcome the techno-economic barriers and potential environmental impacts of the implementation of renewable energy technologies, mostly bioenergy, to tackle climate change and investigating the impact of bioenergy policies on energy security and agricultural development in the rural areas of developing countries. Finally, we will have Dr. Angela Miñas from the University of Manchester. She is a social scientist in the field of agriculture and low carbon energy based at the Tyndall Center for Climate Change Research. She applies her interdisciplinary expertise to study social innovation and uses participatory methods and social network research to identify co-development strategies for climate action and low carbon solutions. Her current projects are part of the Economical and Social Research Council at the Center for Climate Change and Social Transformation. Angela has professional experience in knowledge management and communication, working on themes such as agriculture, climate change, and natural resource management. She has worked on a number of projects in Asia and Africa, exploring social learning in agricultural innovation systems, women in fish farming in Tanzania, participation in community-based forest management in the Philippines, and climate change adaptation and mitigation in Indonesia. Well, no more talking from my side, and now let's hear from our experts. And the first is going to be Dr. Andrew Walfall. The audience is all yours. Andrew, okay.
Okay, ready to go, are you? Can you see everything? Okay, thank you very much for that really grand introduction, and it's really wonderful to be joining you today from the UK. Today I'm going to be talking to you about the role of bioenergy in the UK's pathway to net zero emissions, to try and give you a background of what's going on in the UK in the space of bioenergy and our fight against climate change, but also hopefully there'll be some transferable bits and pieces along the way where we can maybe, where you can find common ground. So yeah, thank you very much. But before I get started, I'll just introduce where I am. I'm sat right here at the minute in Manchester. Manchester is where that little dot is in the UK, which you might be very familiar with. And that is the University of Manchester. It's quite a city centre orientated university. It's quite got strong links in science and technology, and we like innovation. Manchester is also famously home, or the birthplace of the Industrial Revolution, and probably the starting point where all this emissions stuff started to happen on a large scale. So you could blame Manchester in many ways for many of the problems we're finding at the minute in terms of climate change. But on a more light-hearted note, we're also really famous in Manchester for music. And of course, football is not far from everything in Manchester. Those being our big teams, and myself being very much on the red side of the argument. But enough of that. Today, I'm going to talk to you about, first of all, who I am, where we're from. So I'm sat in a group at Manchester University called the Tyndall Centre, and we're a climate change research group that is basically a network of various different universities, they're listed at the bottom there. And we kind of do research that covers all elements of climate change issues, such as carbon budgets, low carbon fuels, bioenergy perceptions of climate change, you name it. We do research on it in the Tyndall Centre if it's anything to do with climate change. And my research more specifically sits with this other network called the Supergen Bioenergy Hub. And this is basically the UK's network of researchers who work on bioenergy, that is transforming biomass resources into different forms of energy. And we work really closely with industry, we work with governments, we work with NGOs and different stakeholders to try and promote the bioenergy sector in the UK. We have people working at every single stage within the bioenergy process, people who grow things or collect resources, people who take that resource and turn it into valuable fuels, people who turn those fuels into energy, whether it's heat, power, transport fuels, and people such as myself who do lots of analysis, calculating what are the impacts of bioenergy and trying to make it a very viable low carbon alternative opportunity for the UK and others people around the world. So that's where my work sits in Supergen and in the Tyndall Centre. But I'm going to take a big step back now and talk to you a bit about the UK and what's going on there. So the UK has a net zero challenge. And when I say net zero, a few years ago, the UK published the Climate Change Act, which is basically a legal requirement for the UK government to reduce all of its emissions based on 1990 levels to zero by 2050. And that's quite a stringent target for a country like the UK, which is highly industrialized, lots of processes going on. It's pretty tough. And the diagram you can see on the right there, you've got two big stacked columns. You can see for 1990, those are our emissions. The different colors basically demonstrate where those emissions are coming from in the UK. And then step forward almost 30 years to 2018, that's where our emissions in the UK are currently. And as you can see, we've lost about a third, we've cut about a third of our emissions, made good progress in decarbonising electricity, also good progress in decarbonising our manufacturing sector, or some people argue that we've got rid of that and deposited it elsewhere, but we've got an awful long way to go. Because by that target in 2050, i.e. the next 30 years, we need to we need to cut those emissions pretty much all down to zero to meet the target. And as you can see there are certain sections of emissions that are really hard to decarbonize. You can see transport has actually gone up in the last 30 years. Agriculture has pretty much stayed the same. Waste has gone down a little tiny bit. But essentially, we've done all the easy stuff in the UK. And we've got this really looming target for 2050 to reduce emissions. So this is the target is looming over all government departments, all academics who work in the space in the UK. How are we going to get there? And the work I do sits within what I call the biomass sectors. So working on growing biomass, using it for different products, using it for energy, using it for fuels. And I'm going to basically tell a story of how this can play a really significant role for the UK and for other countries around the world. So again, on the left there, you can see the breakdown of emissions in 2018. It's more defined now. So these are where emissions are coming from in the UK. And essentially, we've got wastes at the top, or wastes can be biomass resources. So the biomass sectors, in theory, can have a role in decarbonising elements of that waste, those waste emissions. LULUCF, that's land use change and forestry. That's obviously linked to biomass resources. What can the sector do in that space to try and knuckle down and reduce those emissions? We've got agriculture here. Well, agriculture is intrinsically linked to biomass. It produces all sorts of waste and residues that in theory can be used to produce products or fuels. So yeah, there's an opportunity there to decarbonize agriculture. The next couple are fuels and electricity. Obvious biomass resources can produce biofuels. We can produce low carbon electricity. So there's opportunity there too. And the next three are shipping, aviation, and surface transport, such as cars and trains and stuff. We can produce biofuels in the biomass sector. So again, there is a role for the biomass sectors in decarbonizing those. And maybe the most interesting one is the one at the bottom there, which is the negative one. These are carbon sinks. A lot of work and energy in the UK has been put into at the minute. How can we grow that green block at the bottom there, making it more negative to try and offset some of those emissions above the line, which are really hard to decarbonize. So in a nutshell, what I'm trying to get across is the journey for the UK is going to be really hard at the minute, but the biomass sectors have a really, really important role to play, and in theory can impact all sorts of different sectors if we do it in the right way. And I'm sure there's also lessons we can learn from around the world, and lessons other countries can also learn from the UK. So again, so what is bioenergy in the UK? Currently, it's actually the largest renewable energy technology, although the people on the streets of the UK probably don't associate bioenergy as being the leading technology. It does, in fact, generate over 31% of our electricity in the UK, renewable electricity. It generates over 83% of our renewable heat in the UK, and it provides about 5% of total transport energy. So renewable or bioenergy is a large player in the UK. And the UK government has really strong ambitions to increase that, because bioenergy is one of those technologies that can provide a stepping stone away from fossil fuels, and because it's quite a good transition technology. So bioenergy is really high up on the agenda of the UK strategies for climate change and industrial strategy as a technology we want to pursue. So what does that mean generally? Obviously, if we're going to use more bioenergy and grow the bioenergy sector, we're going to require lots more resources. That's fair enough, but where are those resources going to come from? There's likely going to be competition for those resources. Other sectors might already be using that resource. And if we get that resource to international markets, who are we taking away from, and what sustainability impacts are we generating as a result of that? The bioenergy sector also is going to have to adapt in the future. In the UK, we're throwing lots of energy and money at wind power and other sorts of technology, and bioenergy needs to be part of a wider energy mix to provide that low carbon energy mix for the UK, not as a standalone technology, but it should be working alongside other technologies. And as I said previously, sustainability is key. There's no point in us doing bioenergy or any other renewable technology if it doesn't deliver the carbon reductions that we need to get to that net zero target. So that's the vague journey of what the UK is looking at in the minute and the kind of problems that we're grappling with. Some of the key challenges currently are sufficient supply of feedstocks. So how are we going to ensure that there's enough feedstocks or sustainable feedstocks in the UK to be able to meet our targets of bioenergy? So myself and many of my colleagues across Manchester and across the UK do lots of resource modelling work. So basically we look at geography, whether that's the UK, a different country, or a city-state, or whatever it may be. We look at how much resources available, what kind of biomass is that, what's its current use, and how can it potentially be used better to produce energy from it. So these columns here basically provide ranges and kind of highlight the types of resource that many studies think are most available in the UK. So as you can see on the far left, MSW, municipal solid waste. Lots of studies think that this is a really abundant resource in the UK that we could be using better for energy. The two on the far right are based on agriculture. So these are residues from ongoing activities such as straws, also wastes, so maybe animal wastes. So there's also a pretty large resource opportunity that could come from those types of those sorts of sources that the UK could use better. And these are pretty much the same category of resources that we find again and again available in different countries that are currently not used at all, or used very not enough as a potential resource opportunity. There are also other niche opportunities from the likes of forestry residues, or from industry, whatever that industry may be. So there are resource opportunities out there. We just need to make sure we use them better. The next slide here basically has a snapshot of some other work we're doing currently in Manchester. We do a lot of work of mapping where is that resource, how much is it, if a certain site is in a certain location, what resources are on the doorstep, which resources should a power plant use and what shouldn't they. So as you can see here, just as an example, on the left you've got an example of what crops are available in the east of England. That's sugar beets, for instance. And on the right, all these squiggly lines here are different sites. How can you get that resource from A to B in the most low carbon way, the most economical way? So there's a lot of work going on in the UK. Even though we don't have lots of resource, there's a lot of work trying to mobilize that resource better and trying to maximize it within our battle against that net zero target. This diagram here is quite an interesting one, because at the top there, you've got those big black lines. Somewhere within those black lines is the UK's primary energy demand. So basically, the UK is going to have a demand for energy somewhere at the top there within those black lines. And those red lines at the bottom and the different color lines basically demonstrate, if we use UK resources, how much bioenergy can we generate and how does that map against what our overall energy demand are. And then there's some weird little triangle things for 2020 and 2030. And these are basically interim targets of what the UK would like to do with bioenergy, or how much bioenergy they'd like to generate. So as you can see, bioenergy is going to be only a small portion of the overall demand for energy in the UK. But what the difference between the red lines and the colored lines at the bottom of those triangles basically demonstrates that from UK resources, there's no way we can meet our targets, which means there's a deficit of resource in the UK to meet our high level ambition, which means that we're going to have to get resource from somewhere. And what is the UK doing about that? So that's a concern where lots of communications happening in the minute. That takes us to further afield. So here, obviously, there's the major. It's a bit high level, but essentially, there's lots of resource and a growing market for biomass resource and biomass commodities traveling around the world. You've got biodiesel, bioethanol, both the end products and the feedstock coming from South America. Lots also coming from Southeast Asia. You've got wood pellets coming from the Northern Hemisphere. And essentially, the major trade routes, the vast majority of them are currently headed to Europe. That's good for the UK because we can use that resource. But I'm under no illusion. We've done lots of research in Manchester that suggests there's no reason why these current trade pathways should continue they are. As the world develops, as countries start to look at their own energy strategies, they might start to use their own resources more. So countries such as the UK, which are currently really reliant on imported resource, are probably going to have to look at home more as resource around the world becomes more scarce as people use it at home more. So this is the trade markets are interesting and they're growing. But I think they're also a bit dangerous for countries such as the UK. I know Colombia is probably more blessed with resources than us, but you may or may not want to. You may want to use that resource for your own energy needs at home. So a lot of work I do focuses on using what we have home in the UK much better, or looking at different countries and saying, okay, what resources does a country have? How can that country use their resources better, rather than relying on the massive trade of resources, as is the current trend towards. So the next challenge is basically, what are we going to do? What are we going to produce? What future energy are we going to produce? Are we going to produce fuel? Are we going to produce heat, electricity? Are we going to produce products? So there's lots of questions. But the magic with bioenergy is that there's a high degree of flexibility. As you can see here, this is kind of a matrix. You've got in the green there, you've got different feedstocks. You've got different, in the orange, different conversion technologies. You've got options to capture CO2 or not. You produce all sorts of products. And all sorts of end vectors, whether it's power, heat, or transport fuels. So what this diagram tries to show is that, in theory, there's a technology out there to be able to produce your end product you desire by matching the dots. So bioenergy is unbelievably flexible. Based on the resources you have, in theory, you could produce heat, power, transport fuels by just selecting the correct resources and making sure you're doing things in a sensible fashion. The colored lines between those dots basically highlight some of the work, the focus of the work we're currently looking at in the UK. So we're looking at specific things, but the magic of bioenergy is the degree of flexibility. And so if you have a really big need to decarbonize your heat, there will be a pathway where bioenergy could provide an option for that. The secret is to use the feedstocks which are most abundant to you, most available to you, and selecting the correct conversion technology, which will provide you the best efficiencies. And obviously, if you have the technology, you can also look into CO2 capture. And before you know it, bioenergy can provide a really valuable option for you to decarbonize. So it's really important. A lot of work is put into making these decisions. And the biggest challenge in my mind is delivering emission reductions. There's no point in doing bioenergy here in the UK or in any country in the world, in my opinion, if it doesn't deliver those reductions in emissions compared to conventional fuels, such as the fossil fuels. And it all comes down to this. This is a jazzy version of the carbon cycle. And bioenergy basically sits amongst the carbon cycle and is a key mechanism. So as you can see on the far left, you can maybe interpret that CO2 is released to the atmosphere, i.e. through human activities or through natural processes, and CO2 accumulates in the atmosphere, which is not good for global warming. But there's a magic process called photosynthesis that captures that carbon from the atmosphere. That carbon is captured and stored within plant materials, eaten by animals. Basically, biomass materials are accumulated in living creatures through the power of photosynthesis. At the end of the lifespan of those creatures, those animals, in theory, some of it might be released to the atmosphere or may go into carbon sinks in the ground or the soil. And bioenergy and the bioeconomies kind of short circuit this big cycle. As you can see right in the middle there, instead of letting those organisms die, you can short circuit it. You can harvest the crop. You can take residues. You can produce energy from it, and that short circuits the carbon cycle. So the magic of bioenergy is as long as you're not doing something silly along the way, there should be almost a closed loop, a net balance between the atmosphere and carbon sinks by using bioenergy. And there's an added benefit, in theory, if you can master carbon capture and storage, you can capture the emissions, the CO2 emissions from bioenergy, and store them in long-term storage systems like geological systems, and that will make a net flow of CO2 from the atmosphere to the ground. So bioenergy kind of sits nicely within this CO2 carbon cycle. And the secret of making bioenergy low carbon is making sure you're not doing anything silly and making a net flux from the atmosphere rather than to the atmosphere. And we kind of verify this through lots of work I do, and many of my colleagues in the UK. We do something called life cycle assessment. So we kind of analyze what is going on within a bioenergy system and work out, is it low carbon or not? So within a typical system, you might have a resource that you've grown or is naturally grows that captures carbon from the atmosphere. That resource will be harvested in some way. It'll be transported in some way to a central site. That raw resource will be turned into a product or a fuel. It might be transported again. And then eventually that resource might be converted to energy of some form. And then at the end of that process, there might be some waste that needs to be taken care of. So essentially, at each step here, there will likely be energy used, but there'll be emissions potentially to the atmosphere or capture of emissions from the atmosphere. So what life cycle assessment does is kind of add up all those emissions and work out whether overall, whether bioenergy is low carbon or not. So when you produce that energy, is that energy better or worse than burning a lump of coal, burning some natural gas, a fossil fuel equivalent? And in many, many cases, here's just an example of some results from an LCA assessment. So without going into any details, we looked at can an energy crop be grown in the UK to produce heat? And all those little dots there basically represent the results of the greenhouse gas intensity of the heat generated. And any dot that is below that purple line means that, yes, in theory, we're generating heat with a lower carbon intensity than natural gas, which is the normal equivalent in the UK. So yeah, bioenergy can provide a lower carbon alternative to natural gas in the UK. And that red dotted line is like an ambition for what the UK would like to have its heat at, the carbon intensity of heat in the future. So bioenergy, in theory, can provide, in many cases, a lower carbon option. And in many cases, can provide heat well below standard we would like to achieve. So the bioenergy can provide that really valuable opportunity. This next graph is slightly more complicated, but I think it's really worth understanding what's going on. Essentially, these are the results of more LCA analyses, and you've got 4 sets there of different results. You've got, starting on the far left, you've got bioheat generated from agricultural wastes. The next one is bioheat generating from food wastes. After that, bioheat generated from straw. And finally, on the far right, you've got bioheat generated from an energy crop. And within each of these 2 sets of columns, for each one, the one on the left basically is an analysis of what is the carbon footprint of what would happen with that resource if not used for bioenergy. So, for example, if you focus on the one on the far left, agricultural wastes, animal manure, let's say, if that animal manure was managed in how it is normally, if it's not used for bioenergy, what would the carbon footprint of that be? And then the column next to that, the small blue one, in the case of animal agricultural waste, basically demonstrates what the carbon footprint would be if you were to instead take that resource and use it in a bioenergy pathway. And the magic of this is look at all the colors. The colors basically represent emissions associated with different elements of greenhouse gas inventories. So for bioenergy there, even though we're generating energy and it's an energy process, there are emissions associated with the energy sector. There's emissions associated with wastes, with agriculture, with industry, with land use change. So essentially the footprint, greenhouse gas footprint of bioenergy goes well beyond just energy sector. So that's quite the first interesting thing. The next interesting is there are certain cases, if you are focusing your bioenergy on using materials that have basically a really bad alternative path. For example, if you use your food waste that would otherwise go to landfill, in theory, you're going to mitigate all those emissions that would result from that food waste degrading in landfill. That's that big purple stack there. And if you were instead to put that food waste within an anaerobic digestion system and produce a gas to produce heat from it, you would be massively reducing emissions associated with your wastes in the country, but you would also be producing a low carbon fuel alternative that in theory could also replace a higher carbon fossil fuel. So essentially even though this is quite complicated, it's quite interesting as it shows that bioenergy can provide low carbon options to decarbonizing many, many sectors, sometimes across international borders if you're using resources from abroad, but also it can provide energy with much lower carbon intensity compared to fossil fuels. So bioenergy in theory can be a magic solution if done correctly to contribute to much wider things than just energy. It can provide that magical net zero thing. The final challenge I'm going to talk about today is sustainability. Sustainability is this millstone, this thing that hangs around the neck of bioenergy, especially done at a large scale. And especially as we are doing at the minute in the UK, we're importing lots of resources from abroad. And many organizations say it's not sustainable. Look at the impacts. The impacts are unseen. We need to do things more sustainably. So the secret for people such as myself who try and promote bioenergy and investigate how to make it more sustainable is to first understand what's happening and what can we do there. So this is a bit of a plug, a bit of an advertisement for some work I'm doing currently in the UK. So we've developed a new model called the Bioeconomy Sustainability Indicator Model. And what it basically does is for any bioenergy system, for any biomass resource, any supply chain, we have a suite of over 100 indicators of sustainability. Indicators related to people, such as jobs, related to development, such as infrastructure and energy, related to natural systems, such as land, air, and water. And finally, indicators related to climate change, such as land and emissions. Essentially, we try and cover all the bases of all the sustainability issues that could result from a biomass resource or a bioenergy technology. And what we try and do is map the sustainability of that through this model. And it's calculated in a fancy way by selecting indicators relevant to your project. There's a weighting factor. Some issues are more important than others. And essentially, we come up with a sustainability score or a map for a project. Next slide basically demonstrates one of these maps. And these are quite cool because they look good. But also, there's a radar graph here. Around the edges there, there's all sorts of sustainability issues. Everything I've mentioned from, decent work to jobs to innovation, to soil impact, water quality, etc., all sorts of sustainability issues. And you can see here some really big spikes. So there's some big red spikes. These are areas where a particular project has demonstrated a potential sustainability risk, and also some great green spikes which demonstrate, okay, there's actually a benefit here. So mapping sustainability in this way is really good, because sustainability is not a thing. It's not an end destination. In theory, it's a balance of trade-offs between all these different issues. A bioenergy project is probably not going to be sustainable by ticking being green on every single issue, but in balancing these, that is what sustainability is. By mapping sustainability in a way like this, you can identify those really big risks and target actions to mitigate them. And you can also identify those key benefits and target actions to maximize those benefits and promote them. So we're finding this a really valuable tool, and we're working with people in the UK currently who are using this to model their bioenergy systems to map sustainability. Finally, a further element of that work is linking to the SDGs, the Sustainable Development Goals. So as you can see here, all those issues listed on the left, everything ranging from health to economy to land to governance, these are the sustainability issues that we think are really relevant to bioenergy. On the right, you've got the 17 SDGs, which are developed by the United Nations. These are aspirations that different countries are trying to work to promote sustainable development within their country. And within each of those SDGs, there's a subset of many actions. So for example, each SDG might have 20 different sub-actions. And what we've done, you can see all those squiggly lines between one side and the other. We've gone to try and map where bioenergy can potentially provide an influence on the SDGs. So as you can see there, because of the number of lines present, bioenergy in theory can have an impact on every single one of the SDGs. So if you do bioenergy well, do it in a sustainable fashion, you can have a big factor in promoting sustainable development within your country. On the downside, if you do things badly, you do bioenergy in a bad way, do something terrible to the land, etc., you can also have a negative impact on SDGs. But by mapping these SDGs, it really provides a valuable opportunity to promote bioenergy and to look at the positive wider factors and influences that it can generate. And the influence of bioenergy on the SDGs, by doing this mapping, it's much more prevalent. There's much more potential for positively influencing SDGs more than any other renewable technology, wind power, solar power, etc., tidal power. They simply do not reach all the same SDGs because they don't have the same intrinsic links to all the factors, to people, to land, to ecosystems, to food systems, etc. Bioenergy is sat quite neatly linked to all those factors, so it's intrinsically linked to the SDGs. So let's do bioenergy better. This is my almost final slide. So basically, net zero is going to be incredibly hard to achieve for the UK and for all countries that are on a journey to decarbonisation. But the biomass sectors are really well placed to drive progress, and people such as myself are working hard to make sure that can happen. Sustainable supply of feedstocks is always a challenge, but there's also many resource opportunities there. Whichever country I've modelled, there are resource opportunities that can be and should be used better. But it's really crucial also to design systems that balance future demands. We need to make sure if a country's demand is heat, we design systems that deliver heat. If they want transport fuels, design systems accordingly, and make sure you match up the right feedstocks with the right technologies to get the best efficiencies. From the perspective of net zero, bioenergy is only really viable if it does deliver those reduced emissions. But if it's done well, there are opportunities to decarbonize multiple sectors. And finally, mapping sustainability is a really valuable process. Sustainability shouldn't just be a minimum performance you can achieve, as there are also many benefits that may also be achieved. It might generate better jobs, it may generate wealth, etc. So bioenergy is also something not just to fear about sustainability. We should be maximizing the sustainability benefits and really promoting them. And my final slide is this pretty picture of Buckingham Palace there with the great flags of United Kingdom and Colombia side by side. So you've basically learned from me today that we do lots of work on resource availability assessments, supply chains and technologies. We look at energy scenarios, LCA assessments, sustainability mapping, and that work with the SDGs. So if anyone would like to collaborate with us, it'd be really great to do so. Always looking to do so. I really appreciate you letting me speak to you today. And yeah, please ask me any questions if you have them.
Andrew, thank you very much for your speech. Actually, the questions, we are going to save all the questions for the end of the presentation. So like that, we will allow the people to continue hearing the presentation for the other speakers that we have in our conference. Thank you very much. And actually, I have a couple of questions, but I will wait until the end. Thank you. Now, I would like to bring our second speaker, which is Dr. Samira Garcia, and she will be talking about the use of agricultural residues for energy production in rural areas. Samira, the audience is all yours. Thank you.
Thank you. Thank you very much. I will start sharing.
Pueden bajar.
Okay, give me 1 second. I'll start sharing. Meanwhile, thank you very much for the invitation to join this webinar, and to our guest speakers. Can you see my screen now? I guess you can.
Yes.
Okay, good. That's great. Okay, so yes, thank you for the introductions. I will, as Professor Bula said, I'm going to give a global overview of what has been my research on the bioenergy field, but mainly focus on what I did for my PhD research, which aimed to look at the feasibility of using bioenergy with agricultural residues to support sustainable development in rural areas, using as a case study the gasification of coffee stems to supply energy in these rural areas in Colombia. So we'll go through kind of a research timeline. So from 2015 to 2019, I conducted my PhD research, which I just introduced, which was on bioenergy for sustainable development in Colombia using agri-residues. After that, for a year, I worked as a research associate. I did my postdoc also in the University of Manchester and with my colleagues here in Tyndall Center, which focused more on bioenergy, but now with a new ingredient to this equation, which was carbon capture and storage. And currently, I am working as a professional in research and innovation at Promigas, which is a natural gas transport company, but also looking at expanding their portfolio of energy products and services. So I will briefly introduce on one of those strategic objectives for innovation, which is focused on green gases. So before starting, I will give an introduction, an overview of what were the motivation and rationale for looking at agricultural residues. And of course, I'm from Colombia, but behind that, there is more further motivation to conduct this. And one of these is that so the country is looking to diversify the power mix, but using non-hydro renewable sources. We have a fairly clean grid electricity, but we still use, it's mainly hydro sourced. So we are aiming to try to diversify this power mix using non-hydro renewable sources, and bioenergy is one of them. In rural areas, there is sometimes unreliable access to electricity, and the use of bioenergy using agri-residues could enhance energy security in these areas using distributed generation, so small-scale systems. Also, there is a large potential from agri-residues. As Andrew just mentioned, we are actually blessed in having, and we have a strong agricultural sector, hence we produce a lot of agri-residues that we have the opportunity to use better, and meanwhile displace traditional biomass practices. Finally, we are kind of living, it's a bit controversial, but we are living in a post-Civil War period. And then the governments are aiming to foster policies that support sustainable development and rural development. So we could also take advantage of this. So this is the map of Colombia, and what it's shown here is those brown areas. It's where mostly coffee, which is the case study I use, is being cultivated here. And then now going to this more to the specifics, why using the coffee sector, or why using agri-residues from the coffee sector? So this is a world map of where mainly coffee is grown. As you can see, we have a lot in South America, Brazil being the biggest producer. We also have a big contribution. We were now, if I'm not wrong, in the third place. Vietnam is second biggest producer of coffee. We have some strong production as well in Africa. And as you can see, these are the different species. We mainly produce Arabica. Other countries produce Robusta and Arabica, which is the mixed. And this is, we could see it's mostly located in what it's called the Global South. So there are some socioeconomic motivations. So firstly, global coffee production comes from low middle income countries, as you could see in the map. Also, we have around 125 million people relying on coffee production for their livelihood. And from this big amount of people relying on coffee production, almost 90% of this production concentrates in small coffee farmers. And this the smallest share is of the big landlords owning the big pieces of land. There's also technical and environmental motivation. So one of them is to displace traditional biomass uses, which are polluting and inefficient. So instead of, for example, using it in traditional cook stoves, we could use it whether it's for combustion, gasification, anaerobic digestion. This all depends on the properties of our residue. As I said as well, we have a vast amount of residues in the supply chain. It is estimated that almost 90% of the coffee, so from the bean we have when we collect it up until the coffee cup we have, we produce almost 90% of those becomes residues. And finally, there are particularly coffee stems, which was the biomass I studied. This biomass has suitable properties for thermochemical conversion. Therefore, I used gasification as the most suitable technology to produce bioenergy. I used different approaches. The aim of my research, as I said at the beginning, was to evaluate the feasibility of deploying small-scale gasification technologies using agricultural residues for energy generation in rural areas. And the aim of having a kind of an integrated feasibility assessment was to look at the different sides of the equation and the deployment of the technology. So we went through an agri-residues resource assessment in Colombia. We looked at different resources and then decided to go for the coffee sector for the reasons I just mentioned. We conducted process modeling. So we modeled a gasification system to evaluate the technical performance. We also conduct an analysis of the biomass supply and energy demand, which is key to utilize better the resources and, of course, understand what are the energy needs of the sector, whether it's for a small coffee farm or it's for a bigger coffee farm. We also conducted, and this was, I guess, one of the most important parts of my study and the one I liked the most, and it was to understand the environmental impact. So what were the implications of actually using this residue instead of keeping it in the same use? And finally, we conducted an economic assessment where we look at the cost of producing electricity with this residue rather than using, for example, a diesel-based internal combustion engine to produce electricity, or the grid itself. So I'm going to briefly go through some of the different results. So from the technical assessment, what we mainly wanted to understand was the mass and energy balance of the system. So as you can see here, I think I could use a pointer. Yes. As you can see here, we have the big chunk of biomass energy going in. And as we go through the different conversion processes, then we start reducing. Of course, we have big losses, and that's very common in this type of systems. So as you see, we start converting. So here we have kind of the biomass gasification, and we start converting that biomass into a gas that is suitable for injection in internal combustion engines. And we start having some losses already, but we could also recover some of the low-grade heat. So this gas needs to be cooled down and clean in order to be used in these engines. Hence, we could start recovering some of that low-grade heat and then being able to have a higher energy output. So if we could just use the net power output, we could have around 20 kilowatts of electricity. That's a capacity. But if we also include the heat that could be recovered from, as I said, the cooling and cleaning of that gas, we could increase up to around 60 kilowatts of electricity, and then increase our overall efficiency to around 45%, which is not bad for what we call combined power and heat systems. Still, we have a lot of losses, but well, that's very common within these systems. The important thing is the prior treatment that you have to give to this biomass sometimes, whether it's moisturized or not, the way that it's chipped, and all that affects the overall balance, energy balance. So these are some of the numbers that we could obtain. So in terms of how much producer gas we could have per hour, the efficiencies, the amount of low-grade heat we could recover, etc. So some of our life cycle assessment results, as just Andrew mentioned, the aim of conducting an LCA was to understand and evaluate the net environmental impacts when comparing bioenergy systems with our reference systems. So these are some of the results we obtained, and I'm just going to briefly focus on the numbers on the climate change side. So what we did is we compared how was performing our bioenergy system, here tagged as B, and compared to our reference system. So what is actually happening now, for example, in case A1, what is happening is we are using diesel-based electricity, and we're using that biomass in traditional cook stoves. Instead of that, we could produce 100% electricity with our biomass and switch to a fossil fuel, which would be LPG cooking. That could sound like, okay, that doesn't sound good, but actually the numbers show that we could reduce greenhouse gas emissions up to 48%. Also fossil fuel depletion, because we will be then using, instead of diesel, LPG, and that has different impacts. And very importantly, as you can see here, and that's very important for pollution, and is that we could reduce, in theory, we could reduce particulate matter formation, which is a key factor for indoor air quality. And well, as I said, well, the green numbers are the ones that represent reductions, and the orange ones are the ones that represent, in the contrary, increases. That happened when, instead of replacing diesel electricity, we use grid electricity, which I mentioned at the beginning. It's fairly clean. So in those cases, greenhouse gas emissions actually increase instead of decreasing. So it's very important to always assess the counterfactuals. So what was happening before, or what would be happening with that biomass if we don't use it for our bioenergy alternative. And this graph, again, also shows us what could happen just in terms of greenhouse gas emissions. So I just mentioned case A1, it's a decrease in emissions, but A3, which is this one, it's an actual increase. But then other cases showed good results in terms of overall reduction in greenhouse gas emissions. We then looked at the economic assessment, and then what we aimed to do here was to evaluate the impact of using bioenergy, so not spending money in a diesel-based power system, but instead using that bioenergy to produce the electricity that the farm or the family needs to run their households or their coffee farming activities. So the graph here on the right shows how that, so the first one is bioenergy, the second one is biodiesel. So we plotted the different levelized cost of electricity for different capacity factors, and this means how much we are using that bioenergy system along the year, for example. And as you can see, the bioenergy system has a higher OPEX and CAPEX, so it has more capital expenditure and operational expenditure, and a very low biomass cost. So the fuel, which here is biomass, is very small, or even it could be negligible, because usually it's an available residue in those farms, or has a very low cost. On the other hand, the diesel system has a higher cost, because we do have to pay for the diesel, lower OPEX, and also lower diesel. So as we increase the capacity factor, so as we use more efficiently our bioenergy system, we at some point level our LCOE, our levelized cost of electricity, with the one with diesel, but at a lower capacity factors. It would be really hard to reach that threshold of the diesel cost. Here, it's a very similar graph. Here we just included what would be at that moment, so it was almost more than 1 year ago, was the cost of the tariff of the grid power in Colombia. And also we were here graphing, we plotted here the LCOE using bioenergy, and we then added something else to the graph, and was that, as I mentioned before, using heat, so recovering heat from the low-grade heat from the process could also improve our technical efficiency, but also our environmental impact could be lower, and as well, it could improve the environmental, the economic numbers. So it could, since we integrate the heat, we add sort of a credit. So we reduce the LCOE, as you can see here. So the green line shows no heat credit, the orange one shows the heat credit. And then here we start then reducing a bit more our LCOE, which could be good potentially if we aim to implement those types of systems. So using the most of the energy that the system could produce, it's beneficial in all aspects. Finally, I tried to consolidate or collate actually all the results, looking and try to develop a framework. I call it a multidimensional framework. And the aim of this was to understand the results, put them together, and see how all these impacts on challenges could correlate to SDGs that and Andrew just mentioned, which it's the 2030 agenda of the UN to achieve sustainable development. And I could understand and reflect on how the results of the technical, environmental, economic, and societal implications could correlate to the SDGs and identify synergies and trade-offs. I just mentioned a synergy. So the use of bioheat, integrating bioheat to supply the energy demand could, as I said, improve the technical efficiency of the system, so the energy conversion efficiency. Also, it could reduce even more the greenhouse gas emissions, so improve the environmental performance, and also lower the levelized cost of electricity when using these type of systems. So this is a summary, actually, from what I just presented. So as I said, assessing the feasibility of bioenergy using a multidisciplinary approach, so looking at the technical, environmental, and economic part, and also reflecting a bit more, but it was not an in-depth assessment, using a multidisciplinary approach allows to identify synergies and trade-offs. And this helps us on guiding decision-making and maximize benefit and mitigate challenges when using the systems. It's very important also to understand the rural context and balance energy demands and biomass availability. This will help us to determine the operating scales and increase the system's utilization. So, of course, the same system will not work for the same type of farm, for example. As I said, that are very small usually just do farming. They don't do the processing of the coffee bean. Therefore, they have usually a lower energy demand. But those medium to large scale coffee farms usually have an integrated processing process inside the area, and therefore they will need, besides energy to run their households, they will also need some energy to dry, to grind, etc. I mean, all those energy demands that needs the coffee supply chain until you have a grain that you can sell to the market. Finally, integrating the 2030 agenda for sustainable development when evaluating the feasibility of this type of systems. It's key to understand wider societal impacts and co-benefits and their contribution to tackling sustainable challenges. So for me, it was at the end very important to understand how my work could benefit or not. So how those findings could actually have a meaning in contributing to sustainable development. What should we do or not? What should we aim to achieve in terms of synergies, but also what were the trade-offs of using this technology? Okay, so now I'm gonna briefly move to the second part of this research timeline, and in this part I will not develop. I mean, I will not give much information, but if you're happy to talk later, I'm happy to discuss with you. And there's some also work that you could look into. So this was the part of my postdoc research, which aimed to look at the feasibility of BECCS for greenhouse gas removal. And before that, I will briefly explain what it's the concept of bioenergy with carbon capture and storage. Andrew just mentioned it in one of his last slides, and he was explaining the carbon cycle. So we have bioenergy, right? We grow biomass, whether it's in form of energy crops or agricultural residues. We then convert that biomass into a form of energy through different technologies. We have combustion, fermentation, gasification. And sometimes we need to do some fuel upgrading. We need to do gas cleaning, cooling, liquefaction, etc., depending on our energy vector, which are here, our energy products: heat, biohydrogen, biomethane, synthetic fuels, electricity. So here, up until not including CCS, we could have, depending on how sustainable it is, we could have a neutral carbon cycle. So what it's emitted to the atmosphere, the CO2 that it's emitted to the atmosphere when we burn that fuel, has been already captured when the biomass was growing. When we add the CCS part to this equation, as I was saying, then we could, in theory, have what we call net negative emissions. And that was the aim of this project. Here were the funders, and it was a big team of researchers in the UK. One of my colleagues in the work package that we were conducting were Dr. Miriam Roeder and Dr. Clive Goff. Dr. Miriam from the University of Aston and Dr. Clive Goff also from the University of Manchester. So as I was saying, the aim was to investigate the feasibility of different BECCS supply chains to understand the potential UK contribution by evaluating the potential for carbon capture and greenhouse gas emissions removal. As Andrew also mentioned, there's a big challenge for the UK to reach those net negative emissions target that they have. And they, of course, focusing a lot of their research and efforts in conducting research and starting pilots on BECCS, and also forestation and other form of carbon dioxide removal from the atmosphere. So I'm going to introduce you two of the three supply chains that we evaluated. So one, it's a large-scale forestry residues power plant with post-combustion. So what we were using here is we were mainly modeling. We did also process modeling and life cycle assessment for this. We modeled the combustion of forestry residues and further CO2 capture when we combust when we have that flue gas emission. And of course, we have the output is electricity, and we also have the capture of the CO2 and sequestration and storage actually in underground. Why we look into this supply chain? Well, it's a mature technology, and it's fitting current UK energy infrastructure. In the UK, they have already power plants using biomass and importing residues, as Andrew mentioned. Also, forestry residues is potentially an abundant global resource used currently for UK electricity generation. The second supply chain we look into, as I said, there were three. I'm gonna mention two. The second one was a medium scale one, smaller than the first one. And this one aimed to look at the use of UK grown miscanthus, which is one of the most common bioenergy crops in the UK. And instead of using it just for power generation, then this one would be in a CHP system, which I mentioned at the beginning, which it's the acronym for combined heat and power. So you produce electricity and also heat. The capture process is the same, it's post-combustion. We look at the third one. And why we wanted to look at this one? Well, the CCS integration also could fit with current existing biomass CHP generation technologies. Also, there is the potential of an excess heat available on site, and there hasn't been much work on exploring medium-scale systems. Much of this has been most of the research has been focused on looking at large-scale system, whether for combustion or gasification. So it was interesting to look at medium-scale one. And as I said, miscanthus is a feasible bioenergy crop in the UK. The third one was the use of also a UK-grown biomass. It was willow, but then not combustion, but gasification. And since we use gasification, then our carbon capture and storage technology changed to pre-combustion. So some of the results are here. So the process model in part fit our LCA in terms of how much energy and mass we need for everything. And then these are some of the numbers we could obtain. So here, as you can see on this side, are the contributions of the different stages of the supply chain. So the capture part happens when the biomass grows, when we have the CO2 sequestration. And then we have releases of CO2 to the atmosphere and other gases as well. But we were mainly focusing on CO2. So as you see here, the stage or step within the supply chain that emits the most is the biomass feedstock supply chain, at least for this type of biomass, because as I said, it's imported forestry residues. We have in the second place also the emissions from the energy conversion, and with a smaller share, we have the emissions from the CCS infrastructure. When we balance both, we could obtain actually net negative emissions of around 700, if I'm not wrong, and a capture efficiency of 85%. When we didn't use CCS, so when we have just plainly bioenergy for the production of electricity, as you can see here, well, here we have a higher energy conversion emissions, but I mean the key point here is that we then have net emissions without CCS of around 200. Here it would be kilograms of CO2 equivalent per megawatt hour. For our second system, then we have the CHP plant, a medium scale one. And here, as you can see, well, we could have higher net emissions because we have we have enhanced here, or we have used better our biomass. Also, our emissions from the biomass feedstock are smaller because we are not importing that feedstock. We are using UK-grown miscanthus. And we could also achieve a higher CO2 capture efficiency. Overall, again, the net emissions without CCS would be lower. The key findings from this study were that, well, first, the integration of post-combustion CCS could deliver negative emissions with a carbon capture efficiency of around 80%. And this could justify bioenergy generation in the longer term when it's expected a decrease of the UK electricity carbon intensity. When we use cogeneration of electricity, and when we do cogeneration of electricity and heat using UK-grown biomass, then we could have a lower CO2 emissions as a result of a higher energy conversion efficiency. Also, the CCS integration with CHP could also achieve higher net negative emissions of around 92%. And finally, for this second system, for our medium-scale plant, it's important to match the right market. So a CHP system doesn't work anywhere. So we have to also understand what would be the right market to deploy this type of system, whether it's an industrial process where we have an excess of heat, or and they have an excess of heat from a system, but they also need the heat, process heat, as part of the manufacturing process, for example, or for example, a district heating. And so it's important to match the right market and its energy demand, as I mentioned, in order to maintain a constant capacity factor. As I mentioned, and I went through this part very quickly, there is a paper that we published on this where we explain, well, the three supply chains and provide more details on the results. And finally, least but not last, I'm going to also mention what I'm doing and what my colleagues at the Center for Research and Innovation in Energy and Gas in Promigas are doing. So as I actually started 6 months ago working as a professional in research and innovation, and I also have the hat of project manager. I work on different projects running from innovative storage applications, also energy efficiency, etc. But the aim of this last part was to show what was the rationale for innovating within our group. And it's to build a sustainable future where our energy processes, products, and services create value, added value to our clients, the companies, because Promigas is a portfolio of different companies, and the society itself. Being innovation the bridge that connects our current business, which is natural gas transportation distribution, with a sustainable and more prosperous future. Within the SIEC, which is our research center, we have 3 objectives for innovation. One is to diversify the portfolio to improve the value proposition and the interactions with the clients, make our business more sustainable through the development of new products and services based on low to zero carbon energy, and excel in our operations through the development and adoption of solutions that increase security, efficiency, and flexibility in our operations. But I'm going to mostly talk about diversifying our portfolio and making, again, then the business more sustainable. And that is focused on the renewable gases focus of that strategy. So Promigas and all its allied companies, Surtigas and other CO, GDO, etc., are looking at, so we're having the pipeline, different projects, looking at 4 types of green gases. One of that one is biomethane, produced via the anaerobic digestion of organic matter. Finally, second, the synthetic natural gas, which is bio-SNG, produced from the thermal gasification of organic matter. And hydrogen, which has become quite relevant and important in the country lately, when Colombia, the president, announced the hydrogen roadmap. And Promigas has been quite involved in this part, producing and announcing that it's working on 2 pilots on hydrogen from the electrolysis of water using renewable electricity. And one of those pilots aiming to start operation next year. And finally, ammonia, produced from nitrogen and green hydrogen. So this is, of course, all work in progress, but we are very excited in excelling and producing good results with our research and innovation in this area, in green gases. So that was my last slide. Thank you very much for listening, and happy to reply to your questions at the end. Thank you.
Samira, thank you very much for your speech. Yes, for sure there will be questions about that. And now we will move to our final presenter, which is Dr. Angela Miña. And she's going to be talking about the social role considered for bioenergy, specifically in Southeast Asia. Dr. Miña, the audience is all yours. Thank you.
Thank you very much. I have started sharing my screen. I'm not sure if you can see that yet. Hola, me llamo Angela Miñas. I am working at the University of Manchester, like Samira and like Andrew, rather, and Samira used to be my colleague doing research on bioenergy. They both have presented the technical side of bioenergy, and I'm here to bring in more the social science perspective on bioenergy, particularly looking into the roles of farmers, the local communities on bioenergy development. Before I go on to that, I'd like to introduce to you the Tyndall Center and the Center for Climate Change and Social Transformations, which are research centers that are based in Manchester. So one, and Andrew has mentioned it earlier, we do interdisciplinary research on climate change. And one of the aspects of that is bioenergy along with other renewable energy solutions. The Center for Climate Change and Social Transformations, on the other hand, we still do research on climate change, but the focus is on people as agents of transformations. And our research focus are on 4 main areas, which are food and diet, material consumption, transport, mobility, and heating and cooling. And this is a partnership not only with Manchester, but with other universities and an organization called Climate Outreach. So if there is interest in the work of CAST, and if there's interest in the work, we'll be happy to discuss that towards the end of the presentation or of the session. But for now, what I'd like to bring your attention on is our work on bioenergy. As I've mentioned, focusing on farmers and how do we involve, or why do we involve them in the first place in bioenergy development. And I'll present it in 2 case studies. The first one is on rice straw bioenergy in the Philippines and Vietnam. And later on, we'll talk about Myanmar. These are all countries in Southeast Asia. And a lot of the research that I've done in these areas are on agricultural residues. In the Philippines and Vietnam, we looked at rice straw. This is what's left over. Sorry, let me just go back there. This is what's left over after rice harvesting. And this is a large renewable energy resource, and 731 million tons of rice straw is produced every year. The problem is because there's so many of it, farmers just burn it, and it's not good in terms of contributing to greenhouse gas emissions. It has impacts on farmers' health and pollution. And so there is an opportunity there to look at what can be done with rice straw. In the Philippines and Vietnam specifically, at least 75% of it is burnt every year. And so there is an opportunity for bioenergy, for these agricultural residues to be converted into energy and stop or be an alternative to rice straw burning. But the challenge that we look at here is, how do we engage farmers in their communities? They're the ones growing rice and managing the rice straw. How do we engage them? And the reason why we're doing this is farmers and local communities, I'm sure not only in Asia, but in Latin America or elsewhere in the world where you have farming and agriculture. Unfortunately, they remain marginalized in bioenergy development. They end up to be the group of people that you think last, where in fact we should involve them at the beginning. And we don't know, we have a limited understanding on their role and also that of the local communities. So what we did in our work in Vietnam and the Philippines is to do in-depth interviews. We do a methodology called social network mapping and also participant observation. We interviewed farmers, traders, agricultural machine owners, and lenders. These are all people who work in the agricultural sector in the case study areas that we worked in. And what we found is that there are definitely issues around energy security in relation to affordability of energy. Yes, they will have access to electricity, but it's not something that everyone can afford. It could be expensive for others, and all those that require energy, such as farm machine services, they're not always easy to access or affordable for locals. There's also an issue on the flexibility of energy, of the electricity grid to meet the demand. For example, in one of the areas that we went to in Vietnam, whenever farmers use water pumps at the same time, there are blackouts. It doesn't last for hours. Sometimes it lasts for days. Before, they would say it would last for almost a week. And so that's not good. There's definitely an issue for energy security. And there is a lot of feedstock that's available. As I've mentioned earlier, they just burn it. But there are also things, value-added activities that they do, such as incorporating it into the soil, using it as mulch for vegetables and as a fodder for livestock. And Vietnam, a lot of farmers earn income from using straw for mushroom growing. There's still a lot of bioenergy of rice straw left on the field. And so what we're looking at in this study, and there's a pilot site in the Philippines, the technology is from the UK, but it's adapted to the Philippines. It's ongoing at the moment, and the conversion technology that's being used is anaerobic digestion. The scale is village level, to produce biogas to generate electricity for households and potentially to power agricultural machines such as water pumps. So we're looking at it not only from an energy security perspective, but also from a livelihoods and income perspective, where it could provide income to local communities from selling rice straw, the mulch or the leftover from anaerobic digestion. What's left of that could be used as mulch by farmers. So we're looking not only at providing electricity or energy or improving their access to electricity or energy, but also the potential co-benefits in terms of social and economic aspects. So we know that there's potential, there's rice straw, but what we found when we mapped the social network of farmers are also interesting in a way that these helped us inform how to make up a strategy that actually involves these local people. Here I've encircled the actors that are key to how the rice straw management and agricultural activities in the areas are happening. This is in the Philippines, and you can see one of the things that I'd like to highlight here is that the farmer operates in a different social network than the local government, which could be challenging because farmers would need a lot of support and from local government, and these are also connected to those that can provide financing and funding. There's also an interesting relationship between farmers and agricultural machine owners. The thicker the line is, the more significant the relationship is. So, and this is very much one way. So they definitely need the agricultural machine owner, but the question on affordability, as I've mentioned earlier, is a challenge. They work a lot with farm laborers. And so there is a lot of influencing that's happening here. By influencing, we mean the decisions of the farmers and the laborers, they affect each other. So because harvesting in the Philippines in particular is still done manually, they still don't, the combine harvester, which is a machine that they use, is not widespread. So there is an important relationship here. And sometimes because the relationship of farmers and laborers are very strong, they would still choose to harness this relationship than hire agricultural machines, even if sometimes they can afford it. So there are these challenges around social relationships that farmers value a lot. And these are something that we are considering in developing a social innovation strategy for bioenergy. In Vietnam, the local authority and the Farmers Association are key actors. And it's essential for thinking of a bioenergy strategy and how we will involve this these actors. So what we've proposed in terms of a social innovation strategy for bioenergy is one, I've highlighted a few here. Here on the lower part, you can see that what we are proposing is if there's going to be a bioenergy technology on the ground, it's not only technology developers that should be involved. It's not only the government that should be involved, but rather you have your project implementers. Definitely you need support from farmers and communities. And there should be some form of collective leadership. I've highlighted a few here, which could be key to thinking around how we can involve farmers in bioenergy development. We think about the community. The community is not only geographically related, especially for farming. These are vast areas of farmlands, and it could be covering more than 2 villages. And so there are resources and in these areas, and they could still be considered as community because they would share resources as well. The business model and the scale of the project is also something to consider because not all business models would fit one village and the other. So it should, what we're proposing is to ask questions around what form of energy does the community need and for which purpose? How much rice is available? How should members pay for their service? One other thing that I need to highlight here is alignment of project goals and community needs. I've mentioned earlier that the project in the Philippines on biogas from anaerobic digestion is a collaboration between the UK government and the universities such as the University of Manchester and the Supergen Bioenergy Hub. That's happening in the Philippines. But what we learned is it's very important to align the goals of the project with what the community needs, because more often than not, when the funding stops, everything else are to some extent they don't progress as much as we would like to. And so we want this to be benefiting farmers and local communities beyond the project scope. And this is something that we advocate for, knowing what's needed in the community. How do farmers want to take part? What resources are there? It's looking at the local communities, not only from a perspective that you are doing knowledge transfer. I personally I'm not a fan of the word knowledge transfer or technology transfer, but rather co-development. And this is why we're looking at all these social development strategies. So what we've proposed, for example, in the Philippines, is if there's going to be a bioenergy that's going to be deployed there, and it's already happening, a social enterprise model might be fit. Where locals can pay for a fee for service, and there will be microfinancing schemes. Public-private partnerships could also be a way to go, especially to share investment costs. Agricultural machine owners are important, but these are not cheap. Government agencies can offer training and capacity building, because if farm laborers are no longer needed or for harvesting, for manual harvesting, and they need to be trained or reskilled to use more farm machineries, this is where institutions could be key. In Vietnam, because as I've mentioned earlier, we know that the cooperative or the Farmers Association plays a crucial role. An energy cooperative model could be key to involving the local community in a bioenergy strategy. And a lot of it could be supported by other agricultural businesses in their scheme. I could talk more about that later, but in the interest of time, I'd like to share with you something related on Myanmar. So here in the Philippines and Vietnam, we've looked at rice straw. We've looked at potential ways to involve farmers in a social enterprise for bioenergy or an energy cooperative model. In Myanmar, our interest is to look at rice husk bioenergy. It is another product of agricultural production. I'm sure you know husk. As Samira was looking at coffee husk, this is rice husk, which is a byproduct from the milling. The technology on rice husk development is more advanced than in rice straw, but in Myanmar, it's a bit unique. And I can tell you more about that earlier. But first, this is in terms of location. This is where Myanmar is. So they're all in Southeast Asia. The Philippines is here, Vietnam, and Myanmar. All agricultural countries, very much driven by rice production. So when you talk about agriculture in Southeast Asia, it's rice, and it's the sixth largest rice producing in the world. 50% of the population of Myanmar, is employed in agriculture. But as I've mentioned, it's interesting here, although I've mentioned that the rice husk bioenergy is existing, Myanmar had challenges in terms of socio-political, and I'm sure you've heard of it because recently there was civil unrest in the country again. Because of all this, there have been challenges in infrastructure, facilities, and farming practices in the country remain manual. Again, we're looking at an opportunity here that if access to energy is improved in this area, there could be a lot of opportunities for agricultural mechanization, high quality drying and milling, and value-added processing of rice-based products, contributing to not only agriculture and energy, but also livelihoods of the people. In Myanmar, a lot of biomass or biomass use is traditional, and that means they still burn biomass for heat and for cooking. So only 60% of rural areas have access to electricity. This is a stark contrast to the Philippines and Vietnam, which have around 90%. Vietnam almost 100% of access to electricity. And majority, as I've mentioned, comes from biofuels and waste here, as you can see. Rice husk is also a lot. If we think about it in terms of agricultural residues, there's a lot of potential for it to be used for bioenergy. In 2018 alone, 13 million tons of milled rice results to 3.6 million tons of rice husk every year, which can be used for energy generation. What happens now, it's just on, and it's not good from an environment perspective. So when we looked at the case study of rice husk in Myanmar, the question we really want to ask is how can value-added activities benefit agriculture production and improve livelihood? We went into two areas. This is in the Irrawaddy Delta of Myanmar, which are very agricultural, but also they have fishery sector or fishing sector in there. We did group discussions with farmers and millers because they're the ones managing the rice husk, and did a participatory network mapping. We learned a lot of challenges but on the field. Mainly it's because of access to credit and financing. And more often than not, at least across all the case studies, access to credit and financing is always a challenge, especially when you want to introduce a potential source of technology such as bioenergy. This is the most urgent need of smallholder farmers and millers. Small scale millers, and by small scale millers, we mean like this. If I'm not sure if you can see my pointer, but the third photo on the screen, these are small scale milling. They're in off-grid areas. They're very important to smallholder farmers. If you notice in the map earlier, geographically, they are really far apart. So this is why small-scale millers and small-scale operations are important. However, if they want to upgrade their facilities and use all these rice husks for a bioenergy technology, they need financial and technical support. Another challenge that we found is, although there's a rice husk market, they, for example, they produce, some milling companies produce, or yeah, facilities rather, produce rice husk, charcoal from rice husk, and they are able to sell it. Although it exists, it's still mostly used for traditional biomass use. So if we think about it from an environmental perspective, they're still burning, there's still emissions that are being produced. The millers are willing to participate into rice husk value-added activities, but there's a condition that other actors or businesses can manage the rice husk collection from them. So I've mentioned a lot about feedstock availability, how much agricultural residues are there. But one of the challenges there's a big challenge in collecting and transporting all this biomass to be processed. And this is something that that resonated in our case study in Myanmar. Despite all those challenges, we also found potential opportunities. So we did some value chain mapping, and we said what we've proposed to stakeholders in Myanmar is there is a need to build or strengthen connections between medium-scale millers and local businesses that use rice husks. And these local businesses, for example, would use the rice husk in their factories. And at the moment, there's no clear connection to that. There are some, but we want this to be a stronger, a more stable relationship so that the rice husk market can continue to exist. There's definitely an opportunity to support market development for rice husk and energy generation. And again, going back to the idea of involving communities, there is a need. We felt that there is an opportunity to empower local partnerships within communities to manage husk to energy business models. What I haven't mentioned is in both areas, in both villages that we went to in Myanmar, they are already running a rice husk to energy facility. One area is operating a rice husk combustion, basically they just burn the rice husk and it produces some low volt, not a wide scale energy, but it's enough to power a small village or some houses in the village or some street lighting. The other one is a technology that's developed in Myanmar by locals. It's impressive. It's rice husk gasification. It's community managed, but there's not a lot of that. And what we think is there are definitely opportunities for these technologies to be improved and for the community-based ones to be replicated. What's needed is support. And a lot of that would involve linking farmers to service providers to lower cost of production. And what we've learned is, just to recap from what we've learned on the field, is in addition to access to fair financing schemes, investment and support for millers, for small scale farmers, and supporting community partnerships, there's definitely policy focus on rice husk bioenergy that's needed, especially for countries like Myanmar, where the government or policy are quite influential in the development of the agricultural sector. It is true for many countries, I'm sure, but culturally, in these areas, because of the influence of government and policy, we suggested that, from what we learn in the field, it is essential that policy focus on rice husk bioenergy will actually let this technology be more adapted or widespread, for the lack of the better term. We also proposed that perhaps there could be a stricter implementation of rules against rice husk or wastewater disposal into river systems, because this is what they're doing now. I've only given you a brief introduction of our work in the Philippines and Vietnam and Myanmar, but you can read more about them here. We have a journal article published on our work in the Philippines and Vietnam, and a report which we did with stakeholders in Myanmar. If you want copies, I think they're both open access, but I could also email them to you. I've listed our research partners and collaborators. Not all of them are international partners. And I think this is the beauty of working and collaborating in an interdisciplinary institution, is you get to work with industry partners, local partners, national governments, and we're thankful to be doing that. I guess that's it for me. It's quite short, but I imagine there are a lot of questions. My goal for this afternoon was really to give you an overview of the case studies that we're doing in these countries, and basically bringing the focus on farmers and local communities. Because as I've mentioned earlier, we don't want them to be left out in the bioenergy technology development process. Thank you. If there's, I hope that's not very brief, but I hope that's brief enough to entice everyone and invite questions.
Angela, thank you very much for your presentation. And yes, we have some questions. I would like to take those questions. The first one is for Andrew. Andrew, are you there? Andrew?
Hello. Hi.
Yeah. For example, you were talking about how to reduce emissions using the biofuels and using bioenergy. But let's see it from the other point of view, is what initiatives are being taken by the United Kingdom in order to reduce energy demand? Because when we consider to start reducing emissions, it's not only how I reduce the emissions from the fuel or the energy that I'm producing, but also if I am the consumer, what is my responsibility or what is supposed to be done in order to reduce those energy consumption?
Yeah, I guess, I 100% agree. The best thing to do is not use energy in the first place. So it's not my specialism, but there is also lots of efforts going on in the UK at the minute. For example, things around insulating homes, energy efficiency, etc., etc. We're fortunate enough to be hosting the COP26 climate change event in a couple of weeks, and there's been a flurry of initiatives and money being splashed around such things as insulation, etc. So yeah, I 100% agree. Don't use the energy if you can do it in the first place, and there is lots of work happening in that space. I don't know whether that answers your question specifically, but
I was wondering. Yes, I'm sure that the United Kingdom must be taking some steps in order to reduce energy consumption, because at the end of the day, you need to get the balance. If I'm producing a very low carbon energy, but at the end of the day, I also need to start thinking about how I reduce the energy demand. So I will start producing less and less and less energy, or only producing the energy that I actually need for that.
Mm-hmm. Yes.
Thank you very much. We have a question for Samira. Samira, thank you, Andrew. Samira Garcia. Oops. Master.
Yeah.
Is in your research, what have you found so far when comparing South America rural area with Africa and Southeast Asia? Are they facing the same problems when they come to at the time that they are going to think about using bioenergy? Have you researched on that?
Well, not actually. I haven't looked at other areas, but I closely work with Jella. We were PhD buddies during our 4 years, and yes, we when we could talk and discuss about our work, yeah, there are some common ground problems. I mean, most of the countries are between low and middle income countries, or what it was usually known as developing countries. So there are energy access problems, as Angela also was mentioning. There is not enough participation of the farmers, whether are coffee farmers or rice farmers, within the solutions that are being trying to be deployed. The same thing. I didn't conduct a very thorough social assessment, but I did have the time to visit once Caldas, which is one of the regions where coffee is grown, and yeah, I mean, there's some rejection sometimes of new technologies, and the avoidance of traditional practices. There's a lot of cultural aspects involved there, and yeah, of course, there are energy problems, funding issues, because for sometimes these technologies are very expensive at the beginning. I mean, and because they are not fully deployed in the country, they are not very commercial. We need to start by running pilots. So yeah, there are funding problems, there are any energy access problems. So there are common ground issues, yeah, within the same countries, but each country has their own social dynamics, let's say.
Okay, thank you very much. Angela, Samira was saying, is like, for example, what do you think is the best approach for people to adopt the technology that is proposed, and how can you close that technology gap for the villagers to adopt that technology? Because according to what you were saying, that is an issue.
Yes, it is definitely an issue. And so what we've proposed, at least, and what we've seen done in the project in the Philippines, and to note also that the pilot area there is a project between the UK government and project partners in the Philippines. So it's very much collaborative, a knowledge exchange type of thing. How that's been approached is to involve the farmers at the beginning. You don't, I guess the ideal scenario is, and this is what's happening normally. What's happening normally is we develop the technology and then you bring it on the ground. So what we're proposing as a good approach is to have the conversations with farmers and local communities at the very beginning of the project and say, this is what's going to happen. How would you like to get involved? Especially if the technology is coming from outside their community. It is critical in terms of making sure their involvement is true and for the long term. Otherwise, they will most likely not be happy with it. And we don't want that, especially if you're if you're an engineer or someone who's in the technology development side of things. You do have this really good technology, but we don't want it to be in the end rejected by people who we know could be benefiting. So what we've proposed is to involve them right at the very beginning, ask them how they want to be involved. And the key thing to close this gap is other than
okay.
Yeah.
No, go ahead.
One thing, other than telling them how they want to get involved, provide them with the right support system so that they can be involved. if they need to get involved but need access to financing, this should be offered to them. If they want to be involved but needs access to training or capacity building, training for farmers or for local communities could be part of the bioenergy strategy.
Okay, thank you. I'm going to ask you, the master, to please get all our speakers in the, like they say, súbelos todos, por favor. I'm sorry. We are missing, nos falta, okay. We have a general question, which is, how do you foresee the development of bioenergy in your countries, looking at the roles towards the year 2030, when the COP21 goals, those are the, should be achieved? I would like to ask, what is COP21 actually? And
that was the first one. That was back in Paris.
Can you see the question?
Yes.
Well, I would like, I guess that maybe the question is, how do you see it in the United Kingdom? How do you see that here in Colombia, Samira? How do you see that in South Asia, Angela? The three of you could please give us like what do you think about that?
From the UK perspective, currently bioenergy in the UK, a lot of it is used for power. We have these big, large power stations that used to be using coal to generate power, and many of them have been converted now using wood pellets. So that's the current status of bioenergy on a large scale in the UK. But I definitely do not think that is the future. There are other technologies coming online producing power that we are using a lot of in the UK, wind power being maybe the leading one. So I think that the opportunity for bioenergy in the future in the UK is much more focused. We are a cold country. We need lots of heat. So heat will be definitely the way for bioenergy, but also transport. We are investing a lot of money in the UK, hopefully going to electric cars and all that sort of thing. And people are also looking at hydrogen, but there are definitely opportunities for biofuels, for other transport, for ships, for aeroplanes. So I think bioenergy should be used in a much more strategic way in the future in the UK, alongside all sorts of other technologies. As I said in my presentation, the UK has a finite amount of biomass resource. We need to use that in the best way to fill those gaps that other technologies cannot.
Okay, thank you. Samira?
Yes, sure. Thank you. Well, I see the bioenergy as a big player within achieving emission reductions in Colombia. But so far, I think most of the efforts have been focused in the industry sector. So we, at large scale, we produce biofuels. We grow palm oil and sugar cane to produce bioethanol. But I think there could be more. We could do more regarding the use of agro residues. For example, again, the sugar industry uses a lot of the sugar cane within their own companies for cogeneration, and there's much to be done there. We still have a strong agro-industrial sector. I see, for example, that we have a lot of potential using biogas from manure and then converting that into biomethane. As I last present in my last slide, when I was talking about the green gases that Promigas is investigating, that particular gas, the biomethane, has the capacity to be highly interchangeable with natural gas with the current infrastructure. So I think there's a strong role to be played in order to achieve those goals. But again, that we could do more with agro residues as well, and have a stronger policies behind that, so they can support and incentivize the industry. So I think, there is a big role there.
Okay, and now Angela, please.
I would say something similar in terms of policy support for bioenergy in Southeast Asia, because a lot of light are in renewable other renewable energy technologies such as solar, such as wind, which is rightfully so. Southeast Asia is very sunny, unlike the UK, and you can harvest a lot of renewable energy resource from these sources. But I'd say bioenergy, to some extent, is overlooked, and it's probably what could be an unsung hero of COP21 goals, which is to reduce emissions by 2030. But yeah, so I'd say now that there are more and more projects and more research being done on rice residues, in at least in the Philippines, and those that I know in Vietnam and Myanmar, the opportunity to develop more bioenergy in these countries are growing, and it could be that way that it contributes to reducing emissions, which is very important too, because as I've mentioned earlier, a lot of burning and emissions are happening in these countries as well. So if there's an opportunity for developing bioenergy technology from here that is supported by policy or endorsed by policy, then I think that's the way to go for reaching emissions reductions goal aligned with the Paris Agreement.
Okay, thank you very much. It's 12:15. We're going to have some final remarks coming from our main guest, which is Catherine Acuña. Catherine, please.
Well, again, thank you to Dr. Bula and our special guests for this great participation, and to all of our attendees for joining us in this session of Cátedra Europa. We invite you all to continue supporting the education of talented students through our scholarship fundraising campaign, Más Becas, by clicking on the donations button on the homepage of Cátedra Europa. We also encourage you to stay connected to the rest of Cátedra Europa's events. We wish you all a good day and a great afternoon for our visitors from the UK. Thank you.